Okay, we're going to have a look at the worksheet number 3, the escape velocity worksheet that was set for homework. This worksheet requires us, if we get the worksheet up, to use Wikipedia, and we're going to use Wikipedia only because we're going to use a standard um, data, so the whole class gets the same amount, same values. And I'm going to do the one for Callisto. So we just need to so let's access the data. So we go to Wikipedia, and here's the Wikipedia entry for Callisto. And if we scroll down, we'll go to the physical characteristics. And in the physical characteristics, I've over-scrolled it, we'll find the mean radius, which is here. And let's just get this thing working. The mean radius, which is here, and the mass here. You will also notice that it gives a error of some accuracy, so it's got plus or minus here. Now we're going to ignore that. So in this mean radius here, we're going to look at just this value here. This is telling us that we know the mean radius is 2,410 in a small amount, and we know that within an accuracy of 1.5 kilometres. The same thing with the mass down here. We're going to use just the first part here and the scientific notation at the end. We know this value to that level of accuracy. So we're going to to simplify our calculations, we're going to ignore all the plus and minus parts. So we're going to transfer the data here into our spreadsheet. So not our spreadsheet, into our table. So going back, I'll just now enter the data in for Callisto for the mean solar radius and the mass. So we now put our values in. Now we've got to realise or remember that this value here, the 2,410, is actually in kilometres, and we cannot use that in any formula for the gravitational potential energy unless it is converted into metres. The value here was required to two significant figures, so it was 1.073 or something like that. So I've rounded that to 1.1 as the front part of the scientific notation. So now we've got that entered into our table, we need to work out the EP. To work out the EP, we're going to use the data in our formula for EP. And so we know that the formula for EP is that EP equals minus GM M on R. Okay? And the two M's are the important part. The first M is the capital M, and it's the mass of the planet. And the second M is the mass of the object, which is going to achieve escape velocity. So this is the mass of the object. Now that data for the mass of the object is found in the third column along here, which is unlabelled and unnumbered. So we're going to launch a 60 kilogram object from the surface of Callisto. So popping those in, we're going to calculate EP. So EP would equal minus 6.67 by 10 to the minus 11 times the mass of the planet, which is 1.1 by 10 to the 23 times 60, all over the radius, which is 2,000, just checking it again, I think it's 2,000 um, 410. Now that's kilometres, so I'm going to add 3 more zeros to make it metres. And when I calculate that, um, we get a value of, I'm just going to pause while I calculate. Okay, I've got a value of 182.6, or go 0.7 by 10 to the 6 joules. Okay. Right, so that's placed into our third column here. Now, we now need to work out the fourth column. In the fourth column here, we're asked to find the energy of an object that we need to place into that object as kinetic energy so that it would be moved an infinite distance away. To do this, we have to remember our, oops, sorry, we have to remember um, the idea of escape velocity. That on the surface of a planet, we have a certain amount of EP. And in this case, it's negative 182.7 by 10 to the 6 joules. Okay? And we need to move it to an infinite distance away, where up here, the EP is 0. So the work needed, and this comes from the whole idea that the work is equal to the change of energy states, that we need the final, and the final is a 0 minus subtracting negative 182.7 megajoules. Okay. Now the two negatives cancel in this case, so the work needed is 182.7 megajoules, or by 10 to the 6. So that value here goes into our fourth column as here, and the difference is that the difference between the third column and the fourth column is that they're identical excepting for the value of the negative. Now we need to go to the fifth column, and the fifth column here is basically a repeat of the fourth column. It's reinforcing the fact that if I need 182 megajoules to go, to be left, what does that energy come from? And that energy comes from kinetic energy. So this is going to just simply repeat the same column value as the previous. So it just needs to be reiterated as 182.7 megajoules. Okay, so now we know the kinetic energy needed. We know that the kinetic energy is needed is 182.7 megajoules. So to work out the velocity, the escape velocity required, we're going to substitute the formula for kinetic energy, which is a half mv squared, and that is very importantly a little mv squared. And I'll come back to that in a few moments. So just completing the sentence, and that's by 10 to the 6. Now, I said importantly this is a little m. What is that little m? It's the mass of the object that we are launching into space. It's the mass of, for kinetic energy, it's the mass of the object which is in motion, which in this case is 60 kilograms. So we're going to rearrange this. So I will get v squared. So I'm just rubbing that out so I've got room to move. I'll get v squared would equal 2 times 182.7 by 10 to the 6 divided by the mass, which is 60. And so doing a quick calculation on that, I'll times the value by 2 and divide by 60. I will get 6.1 by 10 to the 6th. Okay. Now, remember, this is the velocity squared, so we simply take a square root, and that will give us colour, V equals the square root of that is 2467. Try to write that better. 2467.5. So we'll just round that to an 8 meters per second, or 2.447 kilometers per second. Okay, which we can go now into our final column over here. Right, that's the way of calculating the escape velocity from first principles, from the values of the mean solar radius and the mass. In questions 2 and that was led through in question 2 and 3. In question 4, we're asked to determine the mean and the mass of these solar objects here, that's Mars, Ganymede, and so on, and we're going to apply the formula. And the formula is down here as the square root of 2gm on the radius from which it's launched. So I'm now going to try and I'll do one for us. I'll just use the same data again. I'm not going to use one of these. I'll use the data from Callisto and see if we get the same value. So going here and using the formula V equals the square root of 2gm on the radius, and using the value for Callisto, that's 2 times 6.67 by 10 to the minus 11 times the mass, and the mass was 1.1 by 10 to the 23, over the radius, which is 2410000, that's square rooting. And this should give us the value straight away if we calculate that. And that is, magically, yes it is, it's 2467.5 or 67.8 meters per second. Okay. So what we've got here is this formula does all of what we just did. That is, take EP and equate it with kinetic energy, and then solve for V all in one go, rather than having to go through the process of multiplying by little m and then dividing it out later on. So the rest of this of that can be now completed down to there. Now looking at question 6 and 7. Looking at question 6, we're asked to calculate the maximum radius of the event horizon of a black hole with mass given as 120 by 10 to the 30 kilograms, given that the escape velocity is the speed of light. So all we're asked here is to find the radius of a event, we'll just call it, it's a black hole in this case, given that the escape velocity is a certain value. So we just simply apply that formula that we have just used, I'll try that again, V equaling the square root of 2gm on R, and m is 120 by 10 to the power of 30. R is what we're asked to calculate, so that's the thing we need to use to find, and V is the speed of light, which is 3 by 10 to the 8th meters per second. So I'm going to allow you to put those values in yourself, but you should get a formula which looks like this before you solve. So popping in the values, just collecting, rubbing a few things out so I can have some space. We'll get 3 by 10 to the 8th, 10 to the 8th equals square root of 2 by 6.67 by 10 to the minus 11 times 120 times 10 to the power of 30 all over R. And this is what we need to solve for, is R. So the first thing we're going to do is square both sides to get rid of the square root, and then we will make R the subject. Okay, and the value of that is given in the answers on that sheet. Finally is question 7, where we have to show the gravitational acceleration on the surface of a planet with mass m and r is given by that. Okay, and then apply that knowledge. So to do this, we realise that we're asked here to do G. Okay, and we have a formula already for G. Okay, and the formula already for G is that we know that G equals capital G, capital M on R squared. So this here is asking us to do a small bit of algebraic manipulation. Okay, so we're going to show that that and this are the same when we use the formula for v squared. So I'm going to start with what we are given. So we've got that v squared, oh sorry, undo that. We've got g equaling v squared on 2r. And we know that v equals the square root of 2gm on r. So v squared would equal 2gm on r. So putting that value over here, we get 2gm on r divided by 2r. The cancellation of the 2's happen, and that gives us gm on, and we get another division by r, so it's r times r on the bottom, which is r squared. And that is the other known formula for G. So we've shown what we needed to show. Finally, we've been asked to use this information to find the gravitational acceleration. So we know the escape velocity is 0.51 kilometers per second. We notice that's in kilometers. And we need to find the radius. So we're going to place the values into that formula over there. So putting those values in, we get G equals V squared on 2R, and that means that 2R would equal V squared on G, and V squared, going back, would be 0.51 times 1,000. So it's 0.51 times 1,000 because that was in kilometres, and we need to square that, over the value for G was 0.72, and then simply we need to divide by 2, so we get R equaling a certain value which is given in the answers. Okay, so don't forget that that is 2R, and we need to now divide by 2 to get our value. Okay, so make sure you do that at the end there. Okay, so that completes that sheet. Okay, thank you.